Welcome back, everybody. We have learned the derivative of vector valued functions. We've learned actually that it's not that bad. I mean, math can be like really scary. I mean, I somehow passed algebraic geometry. It can be real scary. Uh, but this is one of those things where if you've got single variable calculus, you're actually in okay shape because the derivative is take the derivative of the x component, the y component, the z component. But what I want to do now is sort of step back and look at properties that will hold true. And some of them should be very familiar to you from single variable calculus because we're still using those same rules. Like, for example, the constant multiple rule. Except for I'm not going to call it the constant multiple rule. I'm going to call it the scalar multiple rule because that's what you're doing. Remember, r of t is a vector and c is a scalar. You're doing a scalar multiplication, a constant scalar. So we really do still want the constant, but a constant scalar here, multiple rule. And it works just like it does in single variable calculus. If you double your function, you just keep the constant around. Basically exactly as we'd expect. We got a sum and a difference rule. That one unchanged. We've got sum and difference, no notes, just exactly what you'd hope, and you're going to do just fine with the sum and difference rule. I got some good news. Before I go on to the next slide, let me go with some good news. My least favorite rule from single variable calculus is the quotient rule. We do not have a quotient rule. The reason why we do not have a quotient rule is because you can't divide vectors. Vector divided by vector does not exist. So that's exciting, right? We don't have a quotient rule. Bad news, though. There are three product rules because we have three different products, right? This first one is a scalar function. So this is like a single variable function times a vector valued function. So this is scalar multiplication. So this would be something if I had like sine of t times t squared t cubed t to the fourth. And I wanted to find the derivative of that. And so sine of t is this multiplier of all the other ones. And here's the weird thing. There's all sorts of like factorizations you could do. You could just distribute this in and so on. But the product rule works. You remember your single variable product rule that says, hey, you just take the first thing times the derivative of the second and then you switch the roles? Yeah, it works here. No changes, except for the products are these scalar multiplications because you got a scalar valued function times a vector valued function. W times r prime, scalar times vector. W prime times r here, scalar times vector. But the product rule still works. How about dot products? This one is a little bit unusual as well because this derivative here, this is a legit single variable derivative because after you've done the dot product, r dot u, there is no vector remaining. The dot product results in a number. In this case, a function, a scalar function. This left-hand side is pure single variable calculus. You just compute the dot product first, and then you're doing like, hey, a derivative of single variable thing. But it's still a product, and the product rule still applies. Just now it is a dot product rule, and so you got dot products, r dot u prime plus r prime dot u. No changes, just you're still using the r and the u, you're using dot products. And notice that the right-hand side, the dot products will be scalar elements at that point. And we got a third one. At least if we're in three dimensions, we got a cross product. Cross product you have to be careful of because notice that the r is to the left of the u. And so r in any product has to stay to the left of the u. So I've got r and I've got u. And I've got r and I've got u, except for I don't quite have that because I'm doing derivatives and I'm doing the product rule. Yes, that's right. The product rule works for cross products as well. You just have to keep doing cross products. Which is to say that we have three different types of multiplication, three different ways you can multiply different types of functions. You want to be aware of what type of function you're doing, what type of multiplication, what the result is. Always try to keep that in mind, but also the product rule just doesn't care. Product rule just works. Just match the same type of multiplication, keep things in the same order, you're good. Product rule works. I already said there's no quotient rule. I'm very excited about that, but we are going to have another rule here. We're going to have a chain rule. Now, the chain rule is maybe the weirdest one, because here is the thing, that r of t, a vector valued function, has inputs that is a single number, and it outputs a vector. And here's something that means. It means that r of t, well, I can't do, it means that r of, if I have u fitting the same framework, u is our next vector. I don't know why we think the alphabet goes ru, but it does. This composition is not valid. And here's why. U of t is a vector valued function. It takes an input t, and fantastic, and outputs a vector. That means that u of t is a vector, and r says, hey, I need a number as an input, and it's being handed a vector. R doesn't take vectors as inputs. So you can't do this. What can you do? Well, we don't have any functions that can take vectors as inputs, so the only thing we can put as an input is a scalar function. We can put w of t, where the input is a number and the output is a number, and so that output is a valid input, turning around and using it to r. So r of w of t is a valid composition. And as a composition of functions, you can try to do the chain rule. And by the way, the chain rule works exactly as it does in single variable calculus. It's r prime of w of t times w prime of t. It's the derivative of the outside evaluated at the inside times the derivative of the inside. Exactly as single variable calculus. You just need to know that what this is really going to look like here is f prime of w of t, g prime of w of t, h prime of w of t times w prime of t. And that last multiplication, that's a scalar multiplication that's happening there. But yes, we've got a chain rule in a situation where the composition makes sense. If the composition doesn't make sense, you don't have a chain rule, you don't have a composition. I'm going to go to a new slide to do that next one. I'm going to come back and actually copy what I had here so I can put it onto this next slide. Because number 7 is a little bit weird. If a vector has constant length, then it turns out it's always going to be perpendicular to its derivative. This right here is the length of r of t squared, which is basically saying r of t has length root c, so r of t length doesn't change. The direction might change. I'm not saying that the direction can't change, but if the length doesn't, if it doesn't matter what t you plug in, the length is always the same, then it turns out, if that first thing is true, then r is always going to be perpendicular to r prime, no matter what t is. And I want to show you why it's true. Because it's actually just a really cool application of the product rule. I'm going to take this equation. If you know that r of t dotted with r of t equals c, and then I'm going to do the same thing to both sides. I'm going to differentiate both sides. I'm going to do d dt on both sides. This is a valid thing to do. You're allowed to do it. I wrote the c in a color that I didn't want to write it in, but that's okay. R of t dot r of t. Well, guess what? The right-hand side, the derivative of a constant, that's a scalar derivative. That's just a number. That's 0. Derivative of a constant is 0. The left-hand side is a product rule. It is r of t dot r prime of t plus r prime of t dot r of t. Now, those look very similar, and dot products order doesn't matter, so I am allowed to switch the order. So this is r of t dot r prime of t plus r of t dot r prime of t. That still equals 0 because I just switched the order on the second one. This is 2 r of t dot r prime of t. I forgot to write all of the primes. Still equals 0. Divide both sides by 2, and voila. R is perpendicular to r prime if the length doesn't change. So real quick, let's go back to that helix. So this is the helix from a video ago from the beginning of 12.2. But what I really want to focus on is this vector u here, which is this red vector. It is already a derivative here, but that's okay. This red vector is a vector valued function. You plug in a t, you get the red vector, and its derivative is also present. It's this dashed blue one there. It won't always stay dashed. It's dashed because it's below the plane there. But let me turn off the blue for a moment and let me just run this video forward. Pay attention to the length of that red vector. The length is not changing. The direction is very much changing, but the length is not changing. And so by what we said, if the length of a vector is not changing, it should be perpendicular to its derivative. And you can see that very clearly when I come here, that no matter where we are, these two vectors, the red vector and its derivative, the blue vector, which is always pointing to the center here, they are always making a right angle with each other. Even though we're moving through space, if the length of a vector valued function does not change, even if the direction does, it will always be perpendicular to its derivative. Why? Because the product rule. I find that just sort of the coolest thing ever, that's how it works out. Okay, let's jump back into our PowerPoint here so we can actually do an example problem where we compute one of these. I want to do this cross product derivative. And I got a couple of options here. Option 1 is to do it as written. Option 1 is to say, hey, I'm going to find u of t cross u prime of t, which means that really I've got step 0, find u prime of t, then find the cross product, and then differentiate. That's how it's written. Or product rule. I'm going to drop the of t's because we know everything is of t. It still works out fine. The product rule says, hey, we're going to take the first one times the derivative of the second. Now, when I say times, I mean the cross product. When I say the derivative of the second, I mean the derivative of u prime. That's u double prime. Plus the derivative of the first cross the second. There we go. I also want to point out that from our properties of cross products, any vector cross itself is 0. In fact, any parallel vectors have cross product 0. And so this will just be u cross u double prime. So we can compute that instead, and it's possible that that will be faster, especially when you realize that u prime of t is 2t comma negative 2 comma 0, but u double prime of t is just 2, 0, 0, which I'm going to write as 2i. So u cross u double prime is, I'm going to do this in the ijk formulation. T squared I plus, well, minus 2tj plus k cross 2i. Because we get FOIL. We get to distribute. We don't have to do the whole matrix thing because u double prime is so simple here. This is going to be t squared, 2t squared, I cross I. This is going to be minus 4t, j cross I. This is going to be plus 2k cross I. I'm just multiplying things. So for example, for that last one, that's k times 2i cross product. So k's on the left, i's on the right, and the 2 you can put out in front. All of the scalar bits, which are t's, numbers, things like that, come there. I cross I is 0. J cross I, you're going backwards. That's going to be a negative k. So this is going to be positive 4tk. It's two negative signs. One, because there's just a negative sign right here. The other, because jik is going backwards around the loop. Here goes my camera, so we can write this last one. Kij, that's going forward, so this is 2j. And I'll just write that. 0 i's, 2 j's, 4tks. And we've got the answer. Sure, you could have done it option 1, but option 2 works out pretty nicely here, I think. To get 0, 2, 4t, that is the final answer. And it's just taking advantage of the cross product and the product rule as you go through. So what did we learn in this video? Just to sum up, mostly it's just that we have properties of the derivative, and mostly they match up with what you got from single variable calculus. Sum rule, difference rule, product rule, but 3 of them. Just make sure you match the same product. But vector valued functions, you do want to think a little bit. Make sure the input is a number, something that provides a number, not a vector. So that affects the chain rule, that only certain setups make sense as a composition. Only certain setups are valid even to write down, but once you get over that hurdle, the chain rule applies. And it turns out there's some really cool connections and structures like this perpendicular vector thing. If the length of a vector is not changing, it is always perpendicular to its derivative, because the product rule is a thing. Product rule is a great rule. It's not as good as the chain rule, but it's a great rule. That's going to be it for this one. In the next one, we'll cover integration, but here's your sneak preview. It's a lot like differentiation. You just do the x component, y component, z component. I'll see you there. Until then, take care.